Well, welcome everybody. My name is Frank Spivak and I'm with the Energy Conservatory. We have quite a few people in attendance here. We know that there were some issues early on where some people were trying to attend the session considerably before our time slot started. So there were some people that tried to get in before 12:30 Central Time and got knocked out. So just want to apologize to those people. Hope that you were able to join us all at beginning at 12:30. So we think that we want to thank you for your participation in this, and hopefully that the information that you get today is going to be useful and helps you out in your daily practice of taking readings and working with a variety of pieces of equipment. Whether it's hopefully the information that you get from this session certainly is going to be related to our products, but also in general when it comes to accuracy and things like that. It applies to instruments pretty much universally. So with that, we've got a couple minutes after 1 o'clock Central Time, and so we'll get started. Just a couple of housekeeping issues for those joining us. This webinar is being broadcast by computer only, so you can't call in and take part. You do need to use your computer, and if you can't hear, then please look at your computer settings for audio and volume of your speakers. This webinar is being recorded and will be on the TEC website, meaning that we'll have a link on our TEC website for you to look at. We do host all of our sessions on YouTube, and we do have a YouTube channel that allows you to look at all of the various sessions, webinars, and videos that we've developed over the last few years for you to be able to take a look at them at your leisure. We do ask that you put your questions in the Q&A box that you'll see on the right-hand side of your screen. Type those in. We'll try to answer them as best we can during the session. If not, we will continue to work on answering the questions at the end, and when we're done, we will have some, well, sure we'll have some email messages that we'll need to send out to people. So with that, we'll get started here, and this webinar has been approved by BPI for one CEU through BPI. We do know that a lot of people have asked us about ResNet credits. This particular webinar is not approved for ResNet credits. Hopefully in the future we're working on some things that would allow us to hold some seminars and webinars that would give participants ResNet credit, but for now this is only BPI and you would be getting 1 hour of credit. So our learning objectives today, we have 3 main learning objectives. One is to understand the basic terms and understand the differences between them when it comes to accuracy, calibration, and maintenance. We also want you to understand what calibration intervals are, what is done during calibration, and how to do some checks on your own for both the fans and the gauges. We also want you to understand maintenance and the things that can be done by the user, and know when you need to send it back to us for more extensive repair. So those are the 3 things that we hope that you'll take away from this session. So here's our agenda. We're going to be talking about accuracy terms, calibration, both of gauges and fans, and maintenance. And the Energy Conservatory is a manufacturer of the equipment. We do provide technical support to our customers on our blower doors, duct blasters, and all of the equipment that we make, including digital gauges. So we will be covering a lot of things that are generic here when we talk about accuracy. When it comes to some of the calibration checks and maintenance, they're going to be specific to our particular products. There will be similarities to other manufactured items, but for this particular session, we're going to be talking about how to use and how to calibrate and maintain energy conservatory products. So let's look at accuracy and the variety of terms that exist when we're talking about accuracy. Accuracy is kind of an amalgam of a whole series of things when it comes to instruments. We look at error, and there's specific kinds of error. There's a random error and there's fixed error. The issue of precision, calibration. Calibration, when it comes to accuracy, is a little bit different than what people might think of necessarily for calibrating a gauge. There's resolution, there's sensitivity, accuracy, the sum of all those parts, and then we're going to look at comparing a variety of accuracy specifications. Now, the terms that we're going to be discussing and giving you some information about are found for the most part in the standard methods for pressure measurement standard 41.3 2014 produced by ASHRAE. I did have the privilege of serving on this committee as chairperson. We had a lot of great participants on the standard who came from national laboratories. So we hope that this particular standard is something that would be useful for you in the future. But we're going to be covering a lot of the terms that came out of that. So for example, the first one we're talking about is error. And we're going to be talking about random error. And this is what's referred to as a statistical error that's caused by chance and is not recurring. So you can see from the graph that given this plot of values and this 45-degree axis, that you see values that are on both above and below the line, some are on it, and when you see this kind of thing over time, given a situation where everything is controlled, then there's something going on with the errors that you're seeing that really can't be calibrated out. They can't be corrected for. This could be a whole series of things. Could be the electronics that are involved, the sensors, how all of that goes together. So when we're talking about random errors, they are the inherent parts of a piece of instrument that just can't be fixed or adjusted. The next type of error is a fixed or systemic, or sometimes referred to as a bias or an offset. And basically what happens when you're taking a series of readings, you see that they all pretty much line up, but they're not exactly on the true value line. So when we see this kind of error, what we're able to do is correct it through calibration. So this is something that allows the manufacturer to be able to make an adjustment. Much like if you were driving down the road, and some people know that when they pass some of these radar signs, you look at the sign and know that you're traveling at 55, but the radar sign comes up that you're traveling at 52, then in the future you know that you're probably a couple of miles per hour over on your gauge that's on your car versus what is a true value. So people tend to, you can adjust, you can calibrate your driving so that you're able to make that adjustment. So this kind of error is something that manufacturers look at as they go through a product and in their manufacturing cycle and finding out how far off of the true value or actual value that's measured and the indicated value from the measuring device itself. So this is so this can be due to the instrument itself, and sometimes in the technique of measurement. So these can be taken care of by making an adjustment and getting you back into an actual value. Another term is precision, and some people think of precision as the number of decimals, and it's really not. The precision is how often are you able to repeat the same reading over and over again. As you can see from the graph on the left-hand side, this really isn't very precise. The numbers or the values are all over the place, and on the right-hand side you see that they're very closely grouped. Now, in this particular case, they aren't very accurate, but they're very precise. So just understanding that taking a series of readings, repeated measurements of the same characteristic by the same method under the same conditions, what shows up, what are those values? And so we look at that precision and see how closely our instruments are working compared to the known or true value. So calibration, what does that actually mean? It means correcting or determining the error of an existing scale. So in our previous graph here, all we need to do is shift all the values so that they line up with our true or actual value, and that becomes the term calibration. So we're moving from what the natural instrument tends to be at to a place where we want to be able to show something that's more appropriate and more proper. And then resolution. When we talk about resolution, there's actually two different kinds of resolutions to work with. And the first one is that resolution is really the smallest change a sensor is able to detect in the quantity that is measured. We can associate this also with either the gauge resolution or also with the sensor itself. Sometimes the way a sensor is built and the characteristics in how they're manufactured have a different kind of resolution. And what we look for when we evaluate sensors is finding the most amount of resolution. We want to find really, really fine differentiation from one value to the next, because you always lose something. When you start putting it together, put the sensor together with all the other electronics, you start to lose something. So we want to find the best sensor that has the best resolution. And then we want to marry that with the gauge and the resolution of the gauge, meaning what's displayed. What's that value that shows up in front of you when you're trying to take a reading? And so resolution of the gauge usually is reflected as the least significant digit, meaning the number on the far right. So is that number on the far right, is the smallest number just 1 Pascal or 1/10 of a Pascal or 100th of a Pascal? And what we're trying to do as a manufacturer is balance the sensor and display resolution versus the task at hand. What is it that the individual who has this particular piece of equipment, what are they trying to measure, and how do we balance out the resolution of the sensor quality and the display? So for example, we really don't need to have a display resolution of 0.001 or 10,000ths of a Pascal to read 1,000 Pascals. It's just not a realistic balance. So when you're reading 1,000 Pascals, having a display resolution of 1 is sufficient, because now you have a ratio of 1 to 1,000. So we're always trying to balance the capability of a sensor along with the ability of the instrument to display a particular value. And then there's sensitivity. The sensitivity is described as the ratio of the change an indicated value to the quantity that's measured. So for example, when we want to go from one reading to the next, we want to go from 1 Pascal to 2 Pascals, how fast does that sensor change when that particular pressure is applied? And we also want to know how much is needed to make that sensor change from one reading to the next. So if we're reading with sensitivity, if we go from 1 Pascal to 2 Pascals and it takes 30 seconds to make that change from the displayed value versus the actual value, then the sensitivity in that case is really, really low. It's not very good. If, however, the sensitivity means that to go from 1 Pascal to 2 Pascals, it happens in 1/10 of a second, then that's very fast. That's very high sensitivity. Also, how much is it needed to make that change? So does the sensor, when you're making those changes, if you go to 1.5 Pascals on your way to 2, does that change to 2, or do you need to go to 1.8, 1.9 before it actually makes that change to 2 Pascals? So we're looking at the sensitivity and all of the components that are involved in making the device and adding that into our value. This can also be interpreted as a number of readings given over a certain amount of time. So for example, our DG700 displays, the smallest display sensitivity is 1 second, meaning every second you'll get a brand new value. What you don't see behind the scenes is that the processor is taking 10 readings in a given second and then displaying that. So we're trying to, in some cases, slow down the sensitivity. We want to reduce the sensitivity because no one would be able to ever understand a gauge when it's fluctuating 10 times a second. You just never see what that true value is. So we're purposely changing some of the sensitivity so that you can actually get a usable reading. So when it comes down to it, what does accuracy really mean? The degree of conformity of an indicated value to an accepted standard value or true value. So when we talk about standard value or true value, we're then comparing ourselves all the way back to a known value, and that's usually at a national laboratory, such as the National Institute of Science and Technology. In the United States, that is the official repository for all of the what are called primary standards for just about anything, whether it's time or weight or pressure or flow. All of those are kept at the National Institute of Standards and Technology. And so that is what is referred to basically as the standard value or true value. And when we talk about accuracy, the degree of inaccuracy is known as the total measurement error and is the sum of the bias error and precision error. So we're taking all of the things that, all of the terms that I just described, all of that becomes the sum of what's shown on a manufacturer's specification sheet. So a lot of things actually go into create an accuracy statement. All of the sensors, all of the electronics, putting everything together. How fast does it respond? How does the, what's the resolution of the sensor? How does the display resolution work? So all of those things fit into and are summarized on a manufacturer's specification page as quote unquote accuracy. And that value is usually described as a percentage. And we'll get into what the comparisons are with different types of accuracy statements. Now, usually what happens is that when you receive an instrument, when you get an instrument, the real values are shown on the calibration sheet for an individual gauge. And you'll see on one side, one set of columns, you'll see all of the values that your individual gauge will display given a certain amount of pressure. And the next column is what's the standard? What was the value that it was supposed to be? And then you get a difference between the two. And that's what builds up and shows the value for accuracy. So I'm hoping that we have a lot of different terms in here, so I'm hoping this is making sense to everyone, and be happy to answer questions as we go through it now or later. So as an example, here's our standard calibration sheet, and you can see that in this particular column, on the top half, you have is all of the positive polarity, or all of the positive values. So the values from 0 going up. You see that there is the standard values displayed first, and then channel A, meaning that's the value of this particular gauge, serial number 4407. So that particular gauge, in the first instance, the standard is reading 24.3. Channel A is also reading 24.3. So the difference, the percentage difference, is 0. And so what we're looking for when we try to make sure that we have an instrument that meets a 1% accuracy is all of the individual values in this percentage difference. Do any of those values exceed 1%? If any of those values exceed 1%, as far as we're concerned, that means that that gauge is not a 1% accuracy. Now you'll see a number of other things in here, such as the calibration. Those are our internal numbers to tell us how well that the instrument over the entire range is meeting its calibration. So these are just values that we use internally to help ensure that the values that we're seeing on channel A have a proper fit and are working to your benefit, make sure that the instrument is correct. Now the one thing is that there's really no such thing as average accuracy. When it comes to accuracy of a particular instrument, the average accuracy is a statistical terminology, but when it comes to looking at all of the individual values that come on the calibration sheet, average accuracy is not a real thing. You want to look at each individual value, and are all of the individual differences less than 1%. When they are, then you have a 1% accurate gauge. Okay, the next step then is we're going to be comparing accuracy specifications. And there's a few different things to understand here. We have accuracy as a percent of reading, accuracy as a percent of scale. Then there's a combination, which is accuracy as a percent of reading or scale plus a fixed value. And then we want you to understand what the absolute accuracy values mean and how that compares. So if you have one instrument versus another, how does it all compare? So let's talk about the first one, accuracy as a percent of reading. This is the amount of actual error that changes with the value of the reading. Generally, this is better suited when you're trying to read values at the low end of the range. So for example, if we say something is a plus or minus 1% of reading, when we're at 50 pascals, that is plus or minus 0.5. At 100, it's 1 pascal, and at 250 pascals, it's 2.5. So you can see that it's a fixed percentage, but the value increases the higher up you are on the scale. So now let's compare that to accuracy as a percent of scale. Now, for example, let's say that the range of the instrument is 0 to 2,500 pascals, and the accuracy is stated as 0.25% of scale. Your first reaction might be, wow, this is only 0.25% accurate. That's really great. But when we add in this value and talking about scale, this really translates into 6.25 pascals of readings. So what happens is that we sacrifice accuracy at the low end, generally for the sake of having a device that has a really high range. So in this case, when we look at 50 pascals, we translate this 0.25%, this 0.25% of scale, as plus or minus 6.25. And you'll see that it's 6.25 through the entire range. The actual percentage of reading changes then. So at 50 pascals, our 0.25% accuracy of scale is really 12.5% of the reading. So we're mixing up a couple of different pieces of terminology here, scale versus reading. But you should understand what that means, so that when you look at something that has an accuracy of scale, now we have to look at, well, what is the scale? What's the range of that particular product? And then look at that and see how that compares to our regular reading. So usually this kind of value tends to be for more industrial instruments where you have a large range, but no one's ever really going to be reading in the low end of things. So we want to, so that's a safe value, a safe accuracy statement. This next one is a little bit more complex to calculate. And when we have a value that has, you'll see it on some accuracy specifications. Some of them are on capture hoods that are out there, that there is an accuracy of reading, there's a percentage of accuracy of reading plus some sort of fixed value. Now in this particular case I'm using pascals, but it could be CFM, it could be inches of water, it could be anything, feet per minute, the like. So in this particular case, let's just say that the accuracy is plus or minus 1% of reading plus 3 pascals. That then translates into 3.5 pascals at 50, 4 pascals at 100, and 250 pascals is plus or minus 5.5 pascals. So all of these are acceptable accuracy statements. What we're trying to impart to you is that understand what the differences are between these accuracy statements and how they translate to you in your everyday set of readings that you have to take. So again, whether this is pressure readings on your manometer, flow readings with your hot wire anemometer, or with your capture hood, all of these things are, we're not saying that any of them is better or worse than any others, just that you need to understand what those values mean and how it fits back into what you're doing with everyday readings. Now, another thing is that we express everything as plus or minus a certain percentage value. But that then means that there is a range where two instruments, when compared to one another, could actually be correct. So for example, if we take plus or minus 1% at 250 pascals, the range of acceptable values is 247.5 to 252.5. We could have two different instruments sitting side by side. One reads 247.5 and the other one reads 252.5, And while that looks, and when you do the math, it's 2% apart, they are both accurate to 1% because the true value, the standard value is 250, but the gauge might be reading a little bit high, might be reading a little bit low from one instrument to the next. So sometimes this takes place when we talk about 3% of 3% accuracy when it comes to flow with a blower door. And when you're reading 3% accuracy and you're at 1,000 CFM, then that's plus or minus 30, if my math is correct, plus or minus 30. So you could have a reading that's 970 and another reading that's 1,030. Both those values are still statistically within the accuracy of plus or minus 3%, even though they're 60 CFM apart. So hoping this makes sense. So with that, then we'll move on to the gauges and talk about the differences of what is included as far as factory calibration and then also field calibration checks. So factory calibration for energy conservatory products is, and that's what we're referring to there, is the gauge, the DG700, DG500, DG3, and DG700 and 500, not the DG3. That's recommended. They have a calibration once every 2 years. So that means that from the day it leaves us and we've calibrated it, it will still maintain its accuracy barring any severe service, that over time, from now till 2 years from now, 24 months from now, it's still going to read within plus or minus 1%. Now, in all of our testing that we've done, and we've checked the calibration of literally tens of thousands of gauges over time, what we have found with our DG700 product and 500 product is that when you get to that 30-month or 2.5-year period, we start to see a few gauges that start to exceed the 1%. Now, it's not all of them, but it's going to be a small percentage. And as you get further and further out, the chances that more and more gauges will start to exceed the 1% accuracy. So we want to make sure that every 2 years you get that done. Now, when you send your gauge to us, we do a full calibration. So if, for example, we receive the gauge and it might be we do a check before and after, so an as found and an as left. What was the condition of the gauge when it came to us, and then we perform the calibration, and what's it afterwards. So sometimes it could be that you've gone 2 years, and you send that back to us. The as found data shows that all of the readings, the worst reading is going to be maybe 0.5 or 0.6% accurate. We're still doing a calibration to bring that down as close as possible because we know over time those results will start to expand and you're going to get an instrument that is going to go out of calibration at some point. So we take and do a complete recalibration and put in all new values so that the gauge itself is going to be as accurate as possible. So we want to get it down to 0 as much as possible. Now the cost of that is $100. It usually takes us 3 or 4 days. We do still have the option to add crews to gauges, and that includes a new overlay. That's another $100 when that's separate from calibration. And we'll talk a little bit about what happens with when we do repair on some things. One of the questions that we received was, are those results as found reported back to you? The answer is yes. So when you send in a gauge to us, we work on it. And we send it back to you. What you receive are two sheets of paper. One is the as found calibration sheet, meaning what did we see. This serves as a way for you uh, to know whether you should be concerned about the last several readings that you might have taken out in the field. If when we see the as found data and it's 2, 3, 4% out of specification instead of within the 1%, then you might want to consider looking at all of the data that you've done recently and determine whether, um, given that it's now we've measured it as 3% instead of 1, do I need to go back to any of the other values that I've taken to make sure that I actually have done something that's a worthwhile test. So you'll see the data that on the as found, assuming that the gauge still works, that you'll see an as found data sheet, and then the second sheet is as it left, meaning we've done everything, it's ready to go, and you'll see both of those sheets with each gauge. So factory calibration, what does happen? Why do you need that? The sensor that's used in most electronic manometers is a piezoelectric pressure sensor. And there's a small diaphragm that's inside there. And over time, that diaphragm fluctuates by having positive and negative pressure go back and forth on that sensor. And it can essentially stretch that out. It usually doesn't happen, but it's possible. The other thing that affects calibration is the temperature cycling inside of a gauge. So you may or may not have noticed it. You might notice it if you're holding on to it, that when you turn the gauge on, that with the electronics that are running, the sensor, the auto zero valves, the processor, the display, and all that, that internally there is a temperature change. And this is one of the reasons that for doing auto zeroing, is to zero out the temperature effects that take place while the gauge is on. So all of those things can have an effect on the calibration, so all the various components. And so that's why it's recommended that over time that factory calibration be performed. Now, we did have a question of ResNet. Does ResNet still require annual calibration? I believe so. If ResNet changes the wording to whatever the manufacturer's calibration interval states, then it would change based on that. Now, there are some programs that require 6-month calibration, and we'll talk a little bit about calibration checks in a moment. So if they still require annual calibration, you may still have to work with your provider, your ResNet provider, and talk about how to comply with an annual calibration check versus a full calibration. Let's see, another question. I've noticed the average number of units are really out of whack. Have we noticed? Well, it's actually a very small percentage. So how many units actually show up that are out of their calibration, out of that 1%? The number is actually quite small, probably certainly less than 5%, might be 3%. The problem is you never know which 3% of the gauges are going to go out and be beyond that 1%. So that's why we say you should have this done every 2 years. You just never know which ones are going to be the ones that are out of calibration. So other things that take place when we do a factory calibration, we're looking at blown or damaged sensors. We're looking at clogged or damaged auto-zeroing valves. We're looking at battery leakage onto the circuit board, damaged displays or overlay. So when we do a calibration, we're doing kind of a health check of your entire gauge to make sure that it's working properly. And those gauges that do have cruise, that the cruise function works. So we're checking all of that stuff. Even though you may not see it, we're checking those to make sure that everything is still working properly. This picture kind of gives you an idea of what our calibration bench looks like. So in the foreground, you see, excuse me, you see a gauge with pressure hoses connected to it. And to the right of the gauge, you see a number of serial ports. We can do calibration of up to 8 gauges at a single time. But usually when we're doing calibration of individual gauges, they're done one by one. This 8 is usually set up when we're doing new gauges. Now you'll see these 2 cubes, what you see beneath the display. There are 2 black cubes with silver tops and connectors on top of those. Those are actually our pressure calibrators. For those interested, these pressure calibrators generally cost $5,000 to $6,000 a piece. The only time they ever leave our facility is when they go to a calibration laboratory. So we have these and we cycle them back and forth to a calibration laboratory to make sure that they are reading properly, and we're checking those against more of a primary standard, so to again ensure that you're getting the proper readings. So this is generally what we're doing. We do have a custom software value, custom piece of software that does all of the calculations, generates pressure, and looks at all of the different values that are taken over the entire range of the gauge. Some people over time have asked us too, why, when my gauge is repaired, is it necessary to have it calibrated? And this relates to something I mentioned earlier, that when a part is damaged, all of those various components, whether it's the display, an auto-zero valve, or something else in the circuitry, all of those have different values that go into creating the working device. So when we change those, we need to make sure that when it's all done and we've made that replacement of the part, that the gauge still is actually accurate. So factory calibration is always required when we have to do something where we're changing components and parts and things like that. Otherwise, if we just swap the part and got it back out to you, you wouldn't really know, is this accurate? Did you check it at all, or anything like that? So we just make sure that we have to have that recalibration done whenever we're changing parts. The factory calibration check. Let's kind of move from factory to field a little bit here. In our blower door and duct blaster manuals, Appendix A describes how to perform a calibration check in the field. And I'll show that diagram to you in just a few moments. One of the things that we do get questions about is sometimes that the gauge display is locked up. It's not doing anything. And what we recommend to people when we're on the phone with them is to perform a reset. So when you've got the gauge on, for some reason you see all the various icons are showing, and they won't go away. The gauge is probably locked up. So what you want to do is turn the gauge off, remove the battery cover, take out one battery, and I forgot a step in here. Once that one battery has been removed, you want to press the on button and wait for 30 seconds. And this discharges any electricity that's still remaining inside the gauge. So you press and hold the on button for 30 seconds, then replace the battery and cover and turn it on. And most of the time, that will get you back to a functioning gauge. Now, there's times where then you've done a reset, but you get no response from the buttons. Chances are that means that the overlay might be bad, and that you'll need to return that to the Energy Conservatory for repair. Now, here is the diagram of doing a calibration check out in the field. Now, we've seen this occur where some associations may have a gauge that has just been recalibrated. They send it to us, they take that gauge, and before it goes anywhere, they then compare that to all of the other gauges that exist either in that company or at the association or wherever it might be. And so they will do this calibration comparison. And you see that there is a magnehelic gauge here, but that's strictly used as a pressure relief. It's not used for any value at all. These syringes can be commonly found at hobby shops. You don't need a really super big one. You just need one that's generating a little bit of pressure. And what we're looking for is what's the value on the standard DG700, and compare that. We're checking the calibration of the second gauge. So we're taking this and running it. We're basically making a T to 3 different pressure ports. So this is how you would set this up. And we see this done fairly often. Any organization that has a number of gauges, you may, depending on your provider and who's overseeing your work, will accept the fact that you've done this sort of calibration check. You've logged all the data, you've kept it. This is how many times I've tested this gauge. And then over time, they might take the second gauge and send that back to TEC, and then compare the other gauges the next year. So it's just a process where you're able to do that. We also see this when people have some issues out in the field. This is a great way to compare and see what's going on. What is my gauge off, or is the other guy's gauge off? And again, you can find that in the manuals, but you can also find it on our website in the support section. So let's switch to fans. Let me see if there are a couple of questions here. Let's see if I can answer those right now. Is there any way for a technician to test to make sure the DG700 is not out of calibration? If it is, then we would want to send it to be sure it's accurate as possible. Here, I hope that what I've answered on doing a field calibration check might be worthwhile, in that periodically you're sending one gauge back to us, and as soon as it comes back, you compare all of the other gauges. Another question, does the temperature of the gauge storage affect calibration? Generally not. We do have a storage value that's listed on our specification page, so we know that over time at a particular storage value that it's not going to harm it. One of the things about the DG700 is that it does have an LCD. LCD stands for liquid crystal display, so there's only so far you can go. You can't go to -40, that's not really a good number, but under most circumstances, the temperature is not going to be affected for most people. Does the number of uses affect calibration or just time? And it tends to be just time. So whether someone's taking 5 readings a day or 2 readings a week, it seems to be over time that is the real effect of what affects calibration. What do I mean by the overlay? The overlay is where the buttons are on the DG700. So that sheet, we call it an overlay. It's a sheet with all of the electronics to activate a button push. So that's what that means. And so when we do cruise and we upgrade to cruise, then the display or the overlay has the cruise values, the cruise indicators on the display, whereas they weren't there on a previous gauge. Another question. I have two DG700s. One has not been used. Should it be returned every 2 years? Again, kind of going back to the idea that time has an effect. I would still recommend it, but if you're not going to be using it, then you don't need to send it in. How does battery voltage affect accuracy, if any? We want to say that it doesn't affect it at all. When your gauge starts to show low and then eventually cuts out, that means that we've already built in internal values to say that when there's only so much voltage, and I don't remember what the number is exactly, it might be 6.8 volts. If it reaches that value, it can affect reading. So we're just going to stop showing anything. The gauge is going to turn off. So if we get to a point where voltage affects accuracy, we just have the gauge turn off. And so as soon as you put in a new set of batteries, you should be back in shape. What can be used in lieu of a magnehelic? Well, basically any kind of, it's basically the principle of water hammer. So that you can use it directly, but then you need to be a little bit more careful about how fast you push the plunger and the syringe. So any kind of pressure relief device would be useful. Magnehelics tend to be inexpensive, and for that purpose, they're useful. So moving on to let's see, one last question here. Is it possible to check if calibration is needed by connecting a tube from the side to the B side and see if there is a difference? Yes, that is a perfectly valid calibration check just to see what's going on. And all you want to do is just connect. You do want to take you can take a piece of hose and connect from the input to the reference side, and that you want when that's working properly, that should be reading 0. And then you want to check from channel A to channel B, just a single piece of tubing, and across that, and those should be reading the same value. When they read the same value, then both sensors can be. You can see that as a general check that's going to work. And someone also put in here that a longer hose can help prevent overpressurizing during field calibration. That's a great idea. So factory calibration of fans versus special calibration. So in the blower door manual and also in the duct blaster manual, there is a fan calibration, fan configuration and calibration and various parameters. So basically, any of the fans that we're making, we're reading pressure values across that fan, and we're taking that pressure value, and that's where you see in this parameter that there's fan pressure in pascals. We're reading the pressure value, and then because we know the size of the opening and the characteristics of the fan housing itself, that using these numbers applied to the fan pressure will provide a flow value directly in CFM. So these are the factory calibration standards. Now there are occasions when someone will need special calibration. There is one particular standard, ANSI 779, that if you're using some of these tests for say, commercial buildings, and they have to be tested in accordance with the Army Corps. Well, the Army Corps has a strict adherence to ANSI 779, and in that particular standard, that the fan must be calibrated once every 5 years. And what we basically do is take the fan, place it on our chamber, and I'll show you the chamber in a minute, and then determine what are all of the flow values over the entire range of the instrument, over the entire range of the fan. And then those can be used as special calibration numbers entered into either TechTite or TechLog. So what are we talking about with a chamber? This is our chamber here at TEC. You see on the left-hand side, you'll see a fan attached to this big white box. This big white box is basically a settling area. There are a number of screens inside there that break up the airflow so that it's not swirling and it's not on one side versus another. Those screens, then this box then enters into a long cylinder that you see on the right-hand side, a piece of ductwork, and lying against that ductwork are orifice plates. Those orifice plates are the pressure measurement standard. So we are able to put different orifice plates in this flow area of the ductwork, and we measure across that and compare how the fan compares to all those values. And you see a number of pressure gauges here, and our attendant that works on the fan calibration basically changes the orifice plates whenever they're needed when we're changing ranges. But otherwise, it's all automated in ramping up the flow of the fan and comparing all those values to our standard values. Now this is kind of small. One of the previous items showed that the image is a little fuzzy. This is small because there's a lot of data on here. But basically, when a fan gets calibrated, and our chamber is constructed to AMCA 200, AMCA standard 210 specifications, when someone gets this calibration, we take a number of readings throughout the entire range, whether it's open fan, ring A, ring B. We do have options of ring C, D, and E. Those just makes the calibration sheet a little bit longer. And what happens is we now generate new coefficients and exponents that are entered into TechTite or TechLog to ensure that. Most, and I would say 99.5% of the users out there, do not need a special factory calibration. The standard calibration of our devices is sufficient for everyone. So how do you do a field calibration check? There's a couple of ways of doing that. Some of the things that affect calibration basically is the location of the sensor, and in this case you see in the foreground picture the flow sensor of a Model 3 fan. The upper picture is as it is installed. So we want to make sure, we want to take this sensor off, we want to check and look at it to see that there's no leaks in that. And then second, we want to make sure it's in the right location. Certainly you want to make sure that there's no broken flanges or broken or missing blades. That's kind of obvious. But to check a Model 3 flow sensor, basically you take a piece of tubing that connect to the fan pressure tap that's on top of the fan, take some tape, and you tape off the various holes that are on the side of the sensor. You create a vacuum in the tubing using your mouth, you just suck on it, and see if you can get that tubing to stick to your tongue for 5 seconds. If it does, that's airtight. If it does not, that means that there's a leak and you need to replace that flow sensor. It could also be a leak in the tubing, so you want to check that as well. And before you use it, make sure that you remove the tape from the sensor holes to make sure you can read. Now the flow sensor position is what's really critical. The motor mounts that are inside the blower door and duct blaster are adjustable. You do have to take off the exit guard in order to be able to get to those to make that adjustment, but it is adjustable. So if the fan were actually to fall on its face, sometimes the motor will move and you want to get that back in its proper location. So how do we do that? Again, in Appendix A of the owner's manual for the blower door and duct blaster tells you how to do this with some of the drawings. Here's a picture of what we actually mean. So you take a straight edge, in this case we've just got a level going across there, and then what we've done is we've added a piece of metal that's the proper size so that this flow sensor is touching both sides of this level with this added piece of metal, because that's the proper dimension that we're looking for. So as long as the level is touching the sides of the housing, and then the sensor is touching the top of the flow sensor, that's the proper position. And when you do that and you check that on a periodic basis, that helps to ensure that your fan is actually accurate. The critical dimension here on a blower door is 3/16 of an inch. It's a quarter of an inch plus or minus a 16th, so 3/16 to 5/16. As long as you're in that range, then your fan is good to go. The duct blaster does have some additional ways of checking calibration. We have created a calibration plate that's added to the far end of the duct blaster flex duct, and then the instructions will tell you how to adjust it, but when you've reached 25 pascals, your gauge should be reading 106 CFM. So this becomes a really good way to understand what's going on. For the duct blaster, though, we're looking at 3/4 of an inch plus or minus 1/8 of an inch. And so again, we've got a flat edge being this level, and we're balancing it across the housing. And then we're making sure that the very tip of the motor is touching this spacer, and then we know that that's actually in the right location. So some user maintenance. Moving from fan calibration and gauge calibration over to maintenance. In this case, we want to talk about a few things like the visual inspection. As mentioned before, you want to make sure that the flow sensor ring is not cracked or broken. The simplest way to remove that is just take a pair of needle nose pliers and take the spring clips and push down in towards the center, and the flow sensor will come off of the motor itself. For cleaning, we see this occasionally when a fan has a problem where it periodically shuts down all by itself. So when it shuts off by itself, it tends to mean that the temperature sensor that's inside there has been tripped and turns the motor off to cool it. And when the temperature has gone down, the fan will start back up again. So the simplest thing to do is to take a shop vac, take the flow sensor off, take a shop vac, and vacuum out any of the dust and debris that's inside there. You can also use a bit of compressed air to help remove some of that. When that's done, you generally will get rid of that issue with get rid of the issue of the fan shutting off all by itself when it's running. Moving on to some of the parts. On our website, and we continue to update this as soon as we have pictures and things like that, on our website, there's two places. When you click on the products part of the menu, you'll get a list of things like the blower door and the duct blaster and things like that. And on the far right-hand side, you'll see replacement parts. That will lead you to a series of replacement parts for all products. You can also go to the blower door system, and you'll see that there is a link for blower door related parts and accessories. So those are all there, and all of the prices should be up to date and be able to do those. And when you're ready to purchase those, give us a call, and either us or our distributors around the country, and they'll be able to get you the products that you need. Another item on hoses. Now, hopefully you can see that this particular hose has a particularly uneven edge on it. It's a regular edge. And so sometimes if that is not seated properly on the gauge, you can get a leak in there. And so what we want to do is we're going to trim off that edge just using a box knife and then put it back on. The other thing is about the hoses, we want to make sure is that over time, especially when you use it a great deal, putting it on and off of the gauge can split the ends of the hose. And so we want to trim that off maybe once a month. Just take an inch off of the end of the tube and put it back, and you should be good to go. Another important aspect is that you want to make sure that there's no moisture inside the hose. So anytime that there is water, because of the diameter, the small diameter of the hose, if water starts to accumulate, it'll actually block the pressure, and so all your numbers are going to be off. So you want to make sure that that there's no moisture inside there, or certainly any debris. Another thing is to do a pressure test on the hoses on a regular basis just to make sure. So just as you're testing the flow sensor of the blower door, you can seal one end of the hose with your finger and take the remaining end and try to suck on it and see if you can get it to stick to your tongue. If it sticks to your tongue for more than 5 seconds, then you actually have a good hose. So once you've gone past that, then chances are, if you need something else, then you probably are going to have to send the gauge or the fan back to us. On our website, we do have this equipment service form for calibration and repair. We ask that you fill that out as best you can. It gives you the shipping address, a little bit of information for those that send things back, and certainly when we do calibration, all the return shipment by UPS is included in that cost of recalibration. We do know that when we do have customers who are in Canada, there is, when we do a recalibration, even though it's already your piece of equipment, Canada may want to have their bit of tax on the value of actually doing the repair or recalibration. So we just want to make sure you're aware of that. So this first sheet talks about you and gives us information about you. The second sheet, it talks about the items that you're returning. So if there's anything that you can provide here to help us and our technicians understand what you might be experiencing, then this is the place to put it in here. So for example, if you have an issue that happens every once in a while, an intermittent thing, we want to make sure that you describe it as best as possible so that we can find it, do the same thing. On our website, we do have quite a bit of useful information. We certainly have all of the product manuals and guides are online for you to download. We also have the videos. Again, we have the links for all of the videos that are on our YouTube site. We've been adding extensively to our FAQs and technical support, so you can certainly go there. We've also added a forum for other users, and over time we hope to have more users be there that they can actually add to the conversation and what you would like to know, and ask questions. We do have links to other sites, and you're certainly able to download the latest version of our software. So with that, I'm going to got a few more questions here that I want to try and answer. Is there any way to field calibrate the exhaust fan flow meter? In a way, there is. The exhaust fan flow meter is based on the idea of having an orifice plate, and there's a formula to do that. I don't have that here to show you, but certainly there's a way to do that. But chances are the only way that the exhaust fan flow meter is going to be out of calibration is if there's a hole or the door's damaged or anything like that, because it's still based on a physical size. It's not really going to be anything that's adjustable, that's outside of your control. If you don't have the sliding door in one of those positions, 1, 2, or 3, then that number is going to be off. So we just want to make sure of that. Let's see, what other kind of, is it okay for medical type hose with the equipment? Any kind of hosing is actually acceptable. You do want to use a slightly thicker walled tubing, because if you use a very thin wall tubing, it has a tendency to kink, and when the tube kinks, it's going to generate pressure and therefore throw your numbers off. So medical type hosing is fine. You just want to make sure that it's not kinking. Does the length of the hose make a big difference in readings? Generally, the length of hose doesn't make a difference, even as far as 100, 500 feet, something like that. What does make a difference in the readings is whether that hose has been subjected to temperature variations. Pressure is a very unusual property in that temperature has a huge effect. So for example, we've seen that a length of hose, even if it's 40 or 50 feet, if part of it happens to be in sunlight, that hose, especially darker hoses, will get hotter. And when that happens, your readings are going to be off. So length is less important than making sure that it's the same temperature all the way from one end to the next. Question regarding hauling the blower door fan unit. Is it best upright or flat? We certainly recommend that it's upright. When it's flat, if it bounces, there's a tendency then that might get it out of the motor mount. So we don't have that. You don't want to do that. Does tube length affect the exhaust fan flow meter? Again, the length isn't going to make any difference. It's whether it's exposed to temperature or not. Is the procedure for field calibrating the duct blaster model A different from the procedure for calibrating duct blaster B model? There's only a few of those out there. The procedure is going to be the same, but I'm going to have to say right now it might be a slightly different number but the gauge does have the Duct Blaster A value in there, so that is something that you want to make sure that it's on Duct Blaster A to read that value. And I am pretty sure, I haven't been asked this before, so I don't know that question specifically, but we can add that later on. But it should read the same. Just want to make sure that you have the gauge on Duct Blaster A. I used an EC fan that needed to be hand started with a pencil. Is there a better, quicker, free fix? Appeared to give accurate readings despite the comical startup. What you've experienced is the fact that the motor on the blower door is a capacitive start motor. So underneath the electrical housing, the white box that's on top of the fan is a capacitor. That provides enough juice or jolt to get the fan started. When that capacitor goes out, then you wind up having to do the hand start. So we recommend you send it in for us to replace that because we're just dealing with electronic components, and we want to make sure that everything is working properly. But that's really a minor fix for the capacitor that's on top of the fan itself. Question, a little bit different question. Why does the baseline clear when switching mode, as in from pressure flow to pressure flow at 50? We did that primarily as a safeguard because we're not sure who's using it and what they're trying to do. So to be on the safe side, we just had the gauge clear the baseline and start over. We know it's a little bit of an inconvenience, but we hope that it actually helps you with providing more accurate readings. Next question is the Duct Blaster calibration plate you mentioned available on the website. It is there, but in order to buy it, just give us a call or give one of our distributors a call, and they're able to supply that to you. And yes, it's on our website. Doesn't matter how far hosed to outside is. Again, that length is not as important as whether there's been any temperature difference. So for example, today it's about 10 degrees in Minnesota. The more that you have that outside, the more that it can affect that. When you're doing a blower door test, it does ask what the indoor and outdoor temperature is, and that's to compare that density. But if you were just using the gauge as a pressure instrument and you had a majority of the length outside today in Minnesota versus inside, that's going to affect your actual reading. Does variation in the height of the hose make a difference to results? Again, it's more related to temperature. So if there is a big temperature difference based on stack effect from the first floor to say the third floor, then yes, you're going to get a slightly different reading. So you want to try and get rid of that as much as possible. Does windy conditions affect sensitivity or accuracy? Certainly they do. We want to make sure that you have the hose buffered as much as possible from any of the outside air. But sometimes it's just the case where if it's a really windy day, there's really nothing you can do. It doesn't have an effect on the accuracy. What you can do sometimes is just increase the time averaging value from, say, 1 second to long term, and that will balance out all those different sensitivity issues. Does the temperature in the house or outside make any difference in the readings? Again, it's when you're doing a blower door test, and you're using Tektite, it does ask you what the outside temperature is and the inside temperature, and that does have an effect on density, and that will have an effect on the value itself. Is a new DG product coming out with a rechargeable battery, USB. Well, there's nothing. We are working on a few things for a possible new gauge, but nothing to really report until probably later on in the year. So don't have any specific information for you right now, but thank you for the suggestions. Do we have a lighter blower door fan? Well, the one thing about the blower door fan is if you can use a duct blaster fan if you're using a tight house. Certainly you can use the duct blaster as the blower door. You do need a special shroud. You need the fabric that has a smaller opening. Those are available for about $130, but you can certainly use that when you're using it on smaller houses. Let's see, windy conditions. We've experimented with placing the under windy conditions, placing the end of the hose in an empty pop can, and that can have some help. But again, it's not perfect. If you've got 40-mile-an-hour gusts, then there's really not much you can do. So you're just going to have to do the test on another day. Wind follow-up question. Does putting the end of a hose, we just answered that. Question, is iPad software in the works? Well, we do have iTech 700 that's used both for Android as well as iOS, and those are out there. We will be making some improvements soon. Probably in the next couple of weeks, we will have in the Android version of iTech 700 the ability to capture and report data from the from the gauge and be able to send that on. So we're continuing over time. We'll have more software available and apps. Question is, I've heard that if it's windy outside, you can put the end of the hose in a bottle cap. We covered that. You want to try different things, but it's really the kind of thing where you want to experiment. But if it's a really windy day, you're just not going to be able to do it. Does multi-point testing compensate for temperature differences in wind? Yes, they will help. Multi-point testing over a wide range can provide that. You do want to make sure that even if it's a very windy day, though, sometimes the scatter or the precision of the readings is so far off that it's difficult to say that it's really accurate. But certainly, multi-point testing is something that works. Duct blaster fan, same as what size opening in a full-size fan? The wording of the question is a little bit mixed up, but I think what the idea is that the duct blaster fan is probably the size of ring B, maybe a little bit larger, but the range is what's important. The duct blaster fan, when used as a blower door, can generate about 1100 CFM at 50 pascals, and that's really what you're looking for. So it's not a whole lot of air, but in houses that are tight, smaller houses, that could be a really useful thing. So with that, I think we've gone way past our time. We really appreciate all of the participants that have been here. Hopefully we've answered your questions. If you do have some questions later on, if you're thinking about it, then please send it on to editor@energyconservatory.com. You can also go to our website and ask a question in the chat function during the day, or just submit a question to us. Thank you again for your time, and appreciate all of the comments and questions. Hopefully this has been worthwhile for you, and you can get a chance to review this webinar later on our website. With that, thanks a lot, and I appreciate your time and consideration today.
Thanks.